In this video, we will discuss the derivative. To define the tangent line to a curve C at a point P on the curve, fix P and let Q be any point on C distinct from P. The straight line passing through P and Q is called a secant line. As the point Q is allowed to move toward P along the curve, the secant line through P and Q rotates about the fixed point P and approaches a fixed line through P. This fixed line, which is the limiting position of the secant lines through P and Q as Q approaches P, is the tangent line to the graph of f at the point P, represented by the line T in the image above. A more precise description of the process of finding the tangent line is as follows. Suppose the curve C is the graph of a function f defined by y equals f of x. Then the point P is described by P of x f of x, or the point x f of x, and the point Q by x plus h f of x plus h, where h is some appropriate non-zero number. We can make Q approach P along the curve C by letting h approach 0. Using the formula for the slope of a line, we can write the slope of the secant line passing through P x f of x and Q x plus h f of x plus h as f of x plus h minus f of x over x plus h minus x, which is equal to f of x plus h minus f of x over h. Q approaches P, and therefore the secant line through P and Q approaches the tangent line T. So we would expect the slope of the secant line to approach the slope of the tangent line. The slope of the tangent line to the graph of f at the point P x f of x is given by the limit as h approaches 0 of f of x plus h minus f of x over h if it exists. The difference quotient of a function f of x given by f of x plus h minus f of x over h measures the average change of y with respect to x over the closed interval x to x plus h. If y equals f of x measures the position of car over time x, then the difference quotient gives the average velocity of the car over the time interval x plus h. It's worthwhile to note that the formula for the difference quotient is exactly the same as the formula for the slope of a secant line as seen before. By taking the limit of the difference quotient as h approaches 0, we obtain the rate of change of f at x. In our car example, this would be the velocity of the car at time x. The rate of change of f at x is often called the instantaneous rate of change of f at x, and is written the limit as h approaches 0 of f of x plus h minus f of x over h. Observe that the formula for the instantaneous rate of change is the same as the formula for the slope of the tangent line. This suggests that the problem of finding the instantaneous rate of change is mathematically equivalent to the problem of finding the slope of the tangent line. The average rate of change of f over the interval x to x plus h, or slope of the secant line to the graph of f through the points x f of x and x plus h f of x plus h, is f of x plus h minus f of x over h. The instantaneous rate of change of f at x, or slope of the tangent line to the graph of f at x, f of x, is the limit as h approaches 0 of f of x plus h minus f of x over h. The derivative of a function f with respect to x is the function f prime, read f prime. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. The domain of f prime is the set of all x for which the limit exists. The derivative of a function f is a function f prime that gives the slope of the tangent line to the graph of f at any point x f of x, and also the rate of change of f at x. There are many notations for the derivative of f. D sub x f of x, dy dx, and y prime are all common, though the last two are used when the rule for f is written in the form y equals f of x. The four-step process for finding f prime of x. First, compute f of x plus h, simplify if possible. Second, form the difference f of x plus h minus f of x, simplify if possible. Third, form the quotient f of x plus h minus f of x over h, simplify if possible. Fourth, compute the limit f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. It is important to simplify at every step to make things easier on yourself. The ultimate plan is to get rid of the h in the denominator before taking the limit. For example, find the slope of the tangent line to the graph of f of x equals 3x plus 5 at any point x f of x. We followed the four-step process. We compute f of x plus h, which is 3 times x plus h plus 5, so 3x plus 3h plus 5. Then we form the difference. F of x plus h minus f of x equals 3x plus 3h plus 5 minus 3x plus 5, which is 3x plus 3h plus 5 minus 3x minus 5, which is equal to 3h. Then we form the difference. F of x plus h minus f of x over h equals 3h over h, which is 3. Finally, we compute the limit f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h, which is equal to the limit as h approaches 0 of 3, which is 3. It makes sense that the slope of the tangent line is a constant here, since any line tangent to a straight line must be that line, and thus must have the same slope as the line itself. The slope of the line f of x equals 3x plus 3x plus 5 is 3. So the slope of its tangent line, which is the same line, must also be 3. Let f of x equal x squared. Find f prime of x and compute f prime of 2. Interpret the result. Using the four-step process, f of x plus h equals x plus h squared, which is x squared plus 2xh plus h squared. F of x plus h minus f of x is x squared plus 2xh plus x plus h squared minus x squared, which is 2xh plus h squared. F of x plus h minus f of x over h equals 2xh plus h squared over h, which is 2x plus h. So f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h, which is the limit as h approaches 0 of 2x plus h, which is 2x plus 0, or just 2x. F prime of x equals 2x, so f prime of 2 equals 2 times 2, which is 4. This means that the slope of the tangent line to the graph of f of x equals x squared at x equals 2 is 4, and that the function is changing at a rate of 4 units per unit change in x at x equals 2. Let f of x equal x squared minus 4x. Find f prime of x, find the point on the graph of f where the tangent line to the curve is horizontal, and what is the rate of change of f at this point. To find f prime of x, we use our four-step process. F of x plus h equals x plus h squared minus 4x plus h, which is x squared plus 2xh plus h squared minus 4x minus 4h. F of x plus h minus f of x equals x squared plus 2xh plus h squared minus 4x minus 4h minus x squared minus 4x, which is 2xh plus h squared minus 4h. F of x plus h minus f of x over h equals 2xh plus h squared minus 4h over h equals 2x plus h minus 4. And f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h, which is equal to the limit as h approaches 0 of 2x plus h minus 4, which is 2x minus 4. When a line is horizontal, its slope is 0. So f prime of x equals 2x minus 4 equals 0. If 2x minus 4 equals 0, 2x equals 4, so x equals 2. And when x equals 2, y equals x squared minus 4x, which is 2 squared minus 4 times 2, which is 4 minus 8, which equals negative 4. The point is 2, negative 4. The rate of change of f at this point is 0. Here's a graph of f of x equals x squared minus 4x, that's the red, and its horizontal tangent line at x equals 2, the blue. Let f of x equal 1 over x. Find f prime of x, then find the slope and equation of the tangent line to the graph of f at the point where x equals 1. Again, we use the four-step process. F of x plus h equals 1 over x plus h. F of x plus h minus f of x equals 1 over x plus h minus 1 over x, which equals x minus x plus h over x times x plus h, which equals negative h over h squared plus xh. Now we find the, now we take the quotient f of x plus h minus f of x over h equals negative h over x squared plus xh all over h, which equals 1 over negative 1 over x squared plus xh. So f prime of x is the limit as h approaches 0 of negative 1 over x squared plus xh, which equals negative 1 over x squared. If x equals 1, the slope of the line tangent to f of x is negative 1 over 1 squared, which equals negative 1, and the line goes through the point 1, 1. The line with the indicated slope through this point is y equals negative x plus 2. If a function is differentiable at x equals a, then it is continuous at x equals a. It is important to note that the opposite is not always true. Continuity is a necessary condition for differentiability, but not a sufficient one. There are 3 cases where a function is not differentiable. First, the function is not continuous. Second, the function comes to a corner or kink, a sharp point where the direction changes suddenly. And third, the function has a vertical tangent line. See example 9 on page 148 in the textbook.